Forecasting IoT trends is crucial for research and development, and patent analysis can be a valuable tool in this endeavor. A recent study, The Power of Patents, leveraging text mining and social network analysis to forecast IoT trends, demonstrates the effectiveness of this approach. By analyzing 3697 IoT-related patents from the last 6 years, categorized into 6 technology areas, the researchers identified the main groups active in patent registration using community detection techniques. The technical maturity of these patents was examined, revealing that information services are in the saturation stage, where growth has slowed. In contrast, smart homes, buildings, and smart grid technologies are still evolving, with significant growth potential. This research underscores the importance of patent analysis in understanding IoT trends and highlights the benefits of investing in technologies during their growth phase, when innovation and development are most rapid. The study's findings have significant implications for companies and researchers seeking to stay ahead of the curve in IoT innovation. By leveraging patent analysis, they can identify emerging trends, anticipate future directions, and make informed decisions about where to invest resources. As the IoT landscape continues to evolve, the ability to forecast trends and identify opportunities for growth will become increasingly crucial. The analysis of the patent landscape for the Internet of Things, IoT, technology reveals a diverse range of innovations across various stages in the technology lifecycle. Key technologies such as safety and security, public safety and environment monitoring, and collaborative aware systems are currently in the maturity stage, indicating widespread adoption and development. Patent mining techniques have been instrumental in identifying these trends within the IoT domain. This process involves analyzing patent data using data mining and text mining techniques to identify patterns, trends, and insights. The community detection algorithm used in this analysis helps identify clusters or communities within the patent landscape, signifying areas of high innovation activity. The IoT technology lifecycle, depicted by the SCURV model, consists of 4 stages: introduction, growth, maturity, and decline. The presence of safety and security, public safety and environment monitoring, and collaborative aware systems in the maturity stage suggests a high level of market penetration and adoption. This could indicate a shift towards more specialized or niche applications within these areas, as well as opportunities for further innovation to extend their lifecycle or replace them with newer technologies. Overall, this analysis provides a comprehensive overview of the current state of IoT technology development, highlighting key areas of innovation and market trends. The Internet of Things, IoT, is a network of physical devices that collect, analyze, and share data in real time, aiming to improve our quality of life. This concept was first proposed in 1999 by UTOID Labs. By 2025, over 25 billion connected devices are expected, including houses, phones, automobiles, and factories. IoT offers great potential for reducing costs by improving efficiency and quality of processes. Applications include healthcare, smart homes, Industry 4.0, and more. IoT network management has become a challenging task, especially with the increase in connected devices beyond 5G. Researchers have proposed innovative solutions such as load balancing, energy management, security, scalability, and fault tolerance. The IoT promotes the service industry by prioritizing connection and intelligent components over physical components. It increases economic flexibility, personalization, and the effectiveness of the physical environment. Technology forecasting is a crucial aspect of appraising emerging technologies, determining their future sectors of use, and understanding their development path. This involves identifying and projecting technological trends through techniques like patent analysis. Patent filings provide specific information for decision-makers, serving as a source of knowledge about emerging technologies and breakthroughs. This research examines IoT technology patents to identify trends by applying text mining and social network analysis. The study is structured into 5 sections, starting with a background on IoT, patent analysis, and technology lifecycle. The methodology is presented in Section 3, followed by the results of IoT patent analysis and technology lifecycle forecasting in Section 4. The paper concludes with discussions in Section 5. The Internet of Things, IoT, is a technological platform that converges the physical and virtual worlds through the Internet, integrating intelligent systems and smart devices to enhance our lives. A fundamental IoT architecture comprises four elements: sensors and actuators, data gathering systems and gateways, edge infrastructure, and cloud platforms. IoT expands the current Internet network, encompassing ubiquitous network-connected objects that bridge the physical and digital worlds. Security is a significant concern, as IoT devices utilize sensors to communicate data to the cloud for data analytics and control choices for cyber-physical systems. The concept of IoT emerged in 1998, with Kevin Ashton first using the term in 1999. IoT applications are often described using phrases with the prefix smart, such as smart supply chain and smart cities. The IoT technology prediction forecasts a growth of almost 300%, from 8.7 billion linked devices in 2020 to more than 25 billion IoT devices in 2030. China was at the forefront of IoT application development, with over 3 billion active devices in 2020. IoT devices are prevalent in every industrial sector and retail market, with the retail sector accounting for 60% of all IoT devices by 2020. Effective data management is crucial for IoT services, as most IoT services depend on the server to deliver seamless services to customers. The IoT concept can be viewed from three aspects: Internet-oriented, things-oriented, and semantic-oriented. The Internet-oriented vision focuses on the network and communication aspects, while the things-oriented vision emphasizes the devices and objects involved. The semantic-oriented vision concentrates on the meaning and interpretation of the data generated. The IoT paradigm combines these three basic concepts, as depicted in Figure 2. The evolution of IoT technology is shown in Figure 3, highlighting the growth and development of this field. The Internet of Things, IoT, vision, as depicted in Figure 2, encompasses various dimensions including the physical, cyber, and social spaces. In the physical space, IoT consists of a vast array of devices, sensors, and actuators interconnected for data exchange and processing. These devices can be categorized into three primary tiers: edge devices, fog nodes, and cloud infrastructure. Edge devices, such as sensors and actuators, are responsible for data collection and actuation. Fog nodes, situated closer to the edge devices, perform preliminary data processing and filtering. The cloud infrastructure, comprising data centers and cloud services, enables remote data processing, analysis, and storage. In the cyberspace, the IoT ecosystem relies on various communication protocols, including Wi-Fi, Bluetooth, and LoRaWAN, to facilitate data exchange between devices. Data formats, such as JSON and XML, are used to represent and transmit data. However, the IoT is susceptible to various security threats, including device tampering, data breaches, and denial of service attacks, emphasizing the need for robust security measures. The social space focuses on the human-centric aspects of IoT, including user experience, trust, and privacy. IoT devices and systems must be designed to ensure user trust, transparency, and accountability. Moreover, user privacy and data protection are critical concerns, as IoT devices often collect and process sensitive user information. The IoT vision is further complicated by the need to address various challenges, including interoperability, scalability, and sustainability. Interoperability issues arise from the diverse range of devices, protocols, and data formats. Scalability concerns involve the ability of IoT systems to handle massive amounts of data and support a large number of devices. Sustainability is critical, as IoT devices and infrastructure must be designed to minimize environmental impact. This comprehensive IoT vision highlights the complexities and challenges involved in realizing a ubiquitous, interconnected, and intelligent IoT ecosystem. This section of the research paper delves into the analysis of patents as a source of technological knowledge and a quantifiable result of R&D activity. It outlines 3 steps involved in patent analysis: information preparation, analysis, and knowledge discovery. The paper highlights the importance of both class-level and patent-level components for comprehensive analysis. Structured data such as patent numbers, International Patent Classification, IPC, numbers, filing date, and inventor are considered, along with unstructured data like headlines and abstracts that can provide fresh insights. The use of bibliometric analysis to examine organized bibliographical data and patent citations is discussed, enabling activities like strategic planning, technology management, competition analysis, and R&D unit management. Patents are recognized as the best resources for technology forecasting and its predictions, offering up-to-date information on various technological fields. The paper also presents a patent lifecycle, identifying tasks that can be automated, at least in part, and the most popular jobs for autonomous patent analysis, including supporting activities, patent categorization, and more. Patent mining and social network analysis, SNA, are powerful tools with diverse applications across various fields. Patent mining involves extracting and analyzing patent data to uncover technological trends, identify potential innovations, and understand the competitive landscape. This process encompasses subfields such as patent retrieval, patent valuation, technology forecasting, patent text creation, litigation analysis, and computer vision activities. These subfields are organized hierarchically according to the invention's subject matter, enabling the identification of emerging technologies and assessment of patent application validity. Social network analysis, on the other hand, is a quantitative research technique that examines the interactions between network participants. By focusing on connections between entities such as people, organizations, and communities, SNA simplifies and visualizes complex systems. The primary emphasis of network analysis lies in the phenomena or data represented by connection models. This technique facilitates the determination of network members' responsibilities and positions, as well as the understanding of network behavior. Both patent mining and SNA offer valuable insights into technological trends, competitive landscapes, and social structures, making them essential tools for researchers, policymakers, and businesses. By leveraging these tools, stakeholders can identify emerging technologies, assess patent application validity, understand network behavior, and determine network member responsibilities. The integration of patent mining and SNA can provide a comprehensive understanding of complex systems, informing strategic decision-making and driving innovation. The growth of the field is analyzed through a social network perspective, focusing on relationships between key individuals and crucial historical moments. In social network analysis, centrality measures quantify the relative significance of nodes. Centrality analysis determines how central a component is to a network, using metrics such as degree centrality, closeness centrality, and betweenness centrality. Closeness centrality, defined by equation 1, measures the proximity of nodes, with central nodes able to travel a short distance to any other node in the network. Specifically, CC(I) represents the closeness centrality of node I, N is the number of nodes, and dis(I) J is the distance between nodes I and J. Betweenness centrality, defined by equation 2, is based on the shortest pathways in networks, with the most central nodes lying on these pathways. CB(I) represents the betweenness centrality of node I, sigma jk is the number of shortest paths between nodes J and K, and sigma jk I is the number of shortest paths between J and K that pass through node I. Eigenvector centrality, calculated based on the idea that a node's centrality is inversely correlated with the sum of its neighbors' centrality values, increases when a node is connected to nodes with high eigenvector centrality. Figure 5 schematically illustrates betweenness, closeness, and eigenvector centrality, providing a visual representation of these key concepts in social network analysis. By applying these centrality measures, the analysis highlights the crucial roles of key individuals and historical moments in the growth of the field. The CDBNE model is a comprehensive framework for community detection in networks, designed to identify clusters of highly interconnected nodes. This methodology can be applied to diverse fields, including social networks, citation networks, and biological networks. In social networks, community detection facilitates the identification of groups with similar interests, thereby enhancing product recommendation. In citation networks, it enables the discovery of new research groups and the prediction of emerging trends. For biological networks, it reveals the community structure and development of specific biomolecules. The CDBNE model offers a systematic approach to community detection, leveraging advanced algorithms and techniques from network science and data mining. The text mining process involves examining and transforming unstructured textual data into a format suitable for analysis. Techniques used include pattern matching, topic tracking, summarization, and information visualization. A typical text mining project involves identifying sources, licensing data, data munging, extracting data, curation and preservation, devising models, and publishing. Text clustering, a significant area of natural language processing, helps in grouping comparable texts, reducing the load on news organizations, and developing intelligent information filtering and suggestion systems. The process of text document clustering involves grouping a collection of text documents into hierarchies of semantic clusters for purposes such as information retrieval, document organization, and automated topic extraction. It begins with data collection, where relevant text data is gathered. Data preparation follows, which includes editing the text to remove extraneous letters, punctuation, and stop words, and normalizing the text through lemmatization, stemming, or converting all text to lowercase. Feature extraction is the next step, transforming the text into a numerical image that can be clustered. Techniques such as the bag of words model, word embeddings, and term frequency inverse document frequency, TF-IDF, are commonly used. Clustering techniques like K-means, hierarchical clustering, or density-based clustering are then applied to group the documents into clusters based on the closeness of their features. Cluster evaluation is conducted to ensure the clustering results are accurate and valuable, using measures such as the elbow method, Davies-Bolden index, and silhouette score to select the optimal number of clusters. Finally, the clustering results are interpreted and visualized to understand the data, using techniques like word clouds or topic modeling to visualize the subjects or themes present in each cluster. This process aids in uncovering hidden patterns and relationships within the text data, making it an essential tool for various applications in text mining and machine learning. The technological lifecycle, TLC, is a series of trajectories, each stage differing in technological content and traits. These stages include germination, development, maturity, death, and possibly resurrection. A well-known technique for technology forecasting is the S-shaped curve, with the logistic model being the most suitable option. This model is represented by equation 3, where parameters such as A, B, and K are crucial for determining the stages of the TLC. These parameters are achieved through least squares fitting computations. The paper emphasizes the importance of examining the TLC as a starting point for understanding technological advancement. The development of technology can be categorized into three distinct phases: early development, maturation, and peak. Understanding these stages is crucial in the context of Industry 4.0 research, which is rapidly transforming the manufacturing landscape. Previous studies have employed various methods to forecast future trends and challenges in Industry 4.0. These surveys have analyzed patents and academic papers to identify key areas of research focus. Notably, data-driven text mining approaches, such as latent semantic analysis, have been used to uncover research themes and areas in Industry 4.0 and IoT. These studies aim to elucidate the intellectual structure and research trends in these fields, identifying key areas such as smart factory and new business model. By analyzing the thematic landscape of Industry 4.0 research, these studies provide valuable insights into the trajectory of technological development and its implications for industry stakeholders. The categorization of development stages into early development, maturation, and peak provides a framework for understanding the evolution of Industry 4.0 technologies. This framework is essential for researchers, policymakers, and industry leaders seeking to navigate the complex landscape of technological change. By examining the intellectual structure of Industry 4.0 research, these studies shed light on the key themes and areas that are driving innovation in this field. This knowledge can inform strategic decision-making, policy development, and research prioritization, ultimately shaping the future of Industry 4.0. Blockchain technology has undergone significant analysis, with a particular focus on its classification and trends. A study of the USA patent database reveals that patents related to blockchain are in the growth phase, with the majority falling under the financial sector. Conversely, blockchain technology itself is still in the emergence phase, primarily driven by researchers and inventors. Further examination of the patent landscape indicates a notable shift towards decentralized applications and platforms, with a significant proportion of patents focusing on smart contract development, distributed ledger technology, and cryptocurrency integration. This trend is attributed to the increasing recognition of blockchain's potential in facilitating secure, transparent, and efficient transactions. The study's findings also highlight the dominance of Chinese companies in blockchain patent filings, with a substantial lead over their American counterparts. This is largely due to China's proactive stance on embracing blockchain technology, with the government actively promoting its development and adoption. The analysis also explores the concept of blockchain classification, which is crucial for understanding the technology's evolution and potential applications. A proposed framework for classification categorizes blockchain into three primary categories: public, private, and consortium blockchain. This framework provides a nuanced understanding of the technology's varied use cases, ranging from decentralized finance to supply chain management. The study's results have significant implications for researchers, policymakers, and industry stakeholders, highlighting the need for continued investment in blockchain research and development to fully realize its potential. The field of patent analysis has seen significant advancements in recent years, with various methodologies and case studies emerging. For instance, a data-driven text mining approach using latent semantic analysis, LSA, was employed by Neruda and Ilwagire et al. In 2019 to analyze academic papers on Industry 4.0. Another study by Sujit Bhattacharya et al. In 2020 utilized social network analysis to examine the intellectual structure of IoT using Web of Science (WOS) data. Patent analytics and text mining were used by Bamikan, Bondarti et al. In 2021 to analyze blockchain patents from the World Intellectual Property Organization (WIPO). The methodology section of this research outlines three main stages: data gathering, data processing, and data analysis. Data gathering involves keyword searches for patent information on the lens.org patent index website, a crucial step for identifying relevant patents within a specific subject area. The second phase of this study centers on data preprocessing, with a focus on preparing data for network and text mining. A key component of this phase is the creation of a patent collaboration network, which is achieved through the generation of a communication table. This table consists of columns for origin and destination, reflecting their respective responsibilities, and a weight column that represents the number of patents jointly registered by two parties. This table provides insight into interactions between individuals or businesses involved in patent registration, highlighting the frequency of collaborative efforts. For instance, a weight of 3 indicates that two parties have jointly registered 3 patents. This phase plays a pivotal role in understanding the dynamics of patent collaborations, shedding light on how different entities interact and contribute to innovation within the field. The study leverages Gephi software to create and analyze a network for understanding the growth and trends in Internet of Things (IoT) technology patents. It begins with pre-processing patent titles and abstracts by removing stop words, followed by generating text vectors using the k-means method and clustering patents as shown in Figure 10. The findings are presented through commonality identification tools and a technology lifecycle diagram. The patent data collection process involves extracting information from the lens.org database, which is the largest global patent database providing free access to patent data. Using search terms, Internet of Things, and IoT, a total of 3,697 active patents were identified, revealing a consistent increase in patenting activity related to IoT in recent years. Figure 11. The results of patent document clustering are applied to predict future trends of technologies in each cluster, obtained using the logistic model and Sigma plot software. The growth curve of IoT technology patents in 6 clusters is also presented in Figure 11. This study provides insights into the development and future directions of IoT technology based on patent analysis. Technology clustering is a crucial step in patent analysis, and pre-processing patent titles and abstracts using word embedding facilitates this process. Word embedding, a natural language processing technique, represents words as numeric vectors in a vector space, enabling text analysis where semantically similar words are closer together. In this research, patent titles and abstracts are mapped to n-dimensional vectors of real numbers using word embeddings, achieved through a combination of language modeling operations and feature learning techniques. The All-Mini LML6 version 2 model, developed from the BERT language model, is employed due to its large training dataset of over 73 million articles. The text embedding process is illustrated in Figure 12. Subsequently, patent clustering is performed using the Davies-Bouldin index, a measure of cluster separation and compactness. The index determines the optimal number of clusters in the dataset, with lower values indicating better clustering. In this research, the Davies-Bouldin index is used to find the optimal number of clusters for the patent dataset, with K values ranging from 2 to 11. The resulting Davies-Bouldin values are plotted in Figure 13, and the optimal number of clusters is determined to be 6 based on the minimum value of the index. This indicates that the patent dataset can be optimally clustered into 6 distinct groups. The Davies-Bouldin index values for 2 to 11 clusters provide a comprehensive overview of the cluster names and their representative keywords. A significant cluster is safety and security, which emphasizes the importance of security in IoT BASED applications. This is due to the variety of devices and communication interfaces involved, making it crucial for ensuring the operation and availability of IoT applications. The patent technology within the safety and security cluster has been emerging since 2012 and entered the growth stage in 2018. This indicates a growing interest in securing IoT BASED applications, as well as the increasing importance of this cluster in the field. In summary, the Davies-Bouldin index values highlight the importance of the safety and security cluster in IoT research. The cluster's growth stage indicates a significant focus on securing IoT applications, which is critical given the diverse range of devices and interfaces involved. The research paper identifies 5 clusters of IoT technologies, each representing a distinct aspect of the IoT ecosystem. The first cluster, Security of IoT Technologies, is in its maturity stage, expected to reach patent technology saturation in 2024. Accounting for 17.7% of the patents. The second cluster, Information Services, is also in its maturity stage, expected to reach saturation in 2024, containing 17.7% of the patents. Information services involve assembling sensor data and delivering it to IoT applications for processing. The third cluster, Public Safety and Environmental Monitoring, is in the growth stage, expected to reach saturation in 2024. With 7.3% of the patents. This cluster concerns the protection of people's lives and property from natural catastrophes, law and order incidents, and crimes. The fourth cluster, Collaborative Aware Systems, is in the maturity stage, accounting for 28% of the patents. These systems use information gathered by information aggregation services to make decisions and take actions, used in smart buildings, smart homes, smart transportation systems, and industrial automation. The fifth cluster, Smart Home, Building and Smart Grid, contains 13.2% and 17.7% of the patents, respectively. Smart homes, buildings are remotely operable through computers or smartphones, while smart grids are electricity distribution systems that monitor and respond to local variations in use using digital communications technologies. The authors have analyzed patent data related to IoT technologies over the last 6 years, identifying the current position of each cluster in the SCURV diagrams and listing the current trend in Table 4, with predictions for future trends in Table 5. The analysis of patent data presented in Tables 4 and 5 offers insights into the technology lifecycle stages. Table 4 predicts future trends, categorizing patents into clusters such as safety and security, information services, and smart grid, among others. Each cluster's maximum patent number indicates the peak year of patent activity. The YT value, calculated as the ratio of patents filed in the last year to the maximum, helps determine the technology lifecycle stage. Values closer to 1 indicate saturation, while values closer to 0 suggest emerging or growth stages. Table 5 elaborates on these stages, providing specific years for each cluster's progression through emerging, growth, maturity, and saturation. For instance, the safety and security cluster is predicted to reach saturation by 2024, and the information services cluster has already reached saturation in 2022. This analysis suggests that technologies like smart grid and smart homes, buildings are nearing saturation, while collaborative aware systems and public safety and environment monitoring are still in the growth or emerging stages. The provided page presents a detailed analysis of the distribution and growth trends of IoT and blockchain technology patents across 6 clusters, utilizing logistic growth curve models. Each cluster is represented by a unique equation, F equals A, 1 plus XP, XX0, B, where A represents the carrying capacity, X0 is the inflection point, and B denotes the growth rate. Cluster 0 illustrates the IoT patent distribution from 2010 to 2024, with a carrying capacity of 250 patents, demonstrating a steady increase in IoT patent activity over the years, reaching its maximum capacity around 2020. Cluster 1 shows the distribution of IoT patents from 2006 to 2024, with a carrying capacity of 200 patents, exhibiting a faster growth rate in the initial years but slowing down after 2014. Cluster 2 represents IoT patents from 2014 to 2024, with a carrying capacity of 140 patents, exhibiting a slower growth rate compared to the previous clusters, suggesting a more stable patent activity in this period. Cluster 3, spanning from 2006 to 2024, has a carrying capacity of 500 patents, indicating a rapid increase in IoT patent activity, particularly between 2010 and 2018, before reaching saturation. Cluster 4 and 5 demonstrate similar growth curves, with carrying capacities of 140 and 160 patents, respectively, indicating steady increases in IoT patent activity throughout the years. Figure 14 and 15 illustrate the growth curves of IoT and blockchain technology patents across the same 6 clusters, respectively, providing insights into the development and saturation points of these technologies over time. The curve analysis of IoT technologies, illustrated in Figure 15, reveals the maturity stages of 3 key clusters: safety and security, public safety and environment monitoring, and collaborative aware systems. These clusters are selected for their significance in emerging fields, offering potential for industrial transformation, efficiency improvements, and new business opportunities. By examining the curve, we gain insights into the current state, growth trajectory, and future development potential of these technologies. The maturity stage of a cluster indicates peak growth, with slower future growth expected. In contrast, clusters in the saturation stage continue to grow, albeit at a slower pace due to market saturation and competition. This understanding informs investment decisions, guiding companies to pursue incremental improvements, new applications, or differentiation strategies, depending on their strategic goals, risk tolerance, and market assessment. The patent cooperation network, depicted in Figure 16, consists of 7,545 nodes and 17,247 edges, representing the relationships between individuals and companies that register patents. Each node corresponds to an entity, while edges form when 2 or more entities collaborate on a patent registration. This network captures the connections between entities in the registration of patents. Table 6 presents various network metrics, including the average degree, which is 4.572. This indicates that, on average, each entity cooperates with more than 4 others to register patents, suggesting a high level of cooperation between individuals and companies in joint patent registration. The average weighted degree of the network is 6.83, taking into account repeated collaborations. This implies that each entity has collaborated with more than 6 others in registering patents. These metrics provide insights into the structure and properties of the patent cooperation network, highlighting the extent of collaboration and cooperation among entities in the patent registration process. In the analysis of the network, a low network density value indicates that although each member is connected to more than 4 other members, this number of connections is small compared to the high number of network members. Table 7 highlights key nodes considering their centrality. Notably, SmithNet-M exhibits the highest degree centrality, with 56 connections in patenting the Internet of Things, indicating a high level of influence in the network. Wangjun, on the other hand, demonstrates the highest closeness centrality, suggesting that innovation or new applications will spread rapidly through the network. Additionally, Wangjun's high betweenness centrality makes them a crucial intermediary for establishing cooperation in registering Internet of Things patents. Zhu Ming stands out with connections to more important nodes, as evidenced by their high eigenvector value. To further elucidate the network structure, community detection is employed, identifying subsets of nodes within the graph where connections are denser than those with the rest of the network. The results, presented in Table 8, provide insight into the network's underlying organization and potential collaboration patterns. The community detection analysis reveals 5 distinct clusters, each corresponding to a specific demographic group. The Brown community, labeled as USA companies, comprises 155 nodes and 404 edges, with a density of 0.034, indicating a relatively weak connection between components. Key members include Trim Craig M., Fox Jeremy R., and Bender Michael, focusing on legal matters related to IoT patents. The Blue community, consisting of Chinese companies, has 131 nodes and 740 edges, with a density of 0.087, indicating a strong relationship between components. Notable members include Zhu Ming, Chen Jia, and Zhao Jian, representing Chinese technology companies active in IoT patent registration. The Green community, labeled as Global Companies, encompasses 110 nodes and 562 edges, with a density of 0.094, indicating a powerful connection between components. This cluster comprises individuals with diverse last names, suggesting they come from different companies with various areas of expertise related to IoT patents. Key members include SmithNet-M, Purnashandran Rajesh, and Nolan Keith. The Red community, consisting of Spanish-speaking companies, has 109 nodes and 338 edges, with a density of 0.057, indicating a relatively weak connection between components. Notable members include Xu Hao, Rico Alvarinho Alberto, and Zhang Jing, representing companies based in Spanish-speaking countries and specializing in IoT patents. Lastly, the Purple community, labeled as Chinese tech companies, comprises 109 nodes and 493 edges, with a density of 0.084, indicating a strong relationship between components. Key members include Wang Wei, Miao Weiwei, and Li Wei, representing Chinese technology companies active in IoT patent registration. The analysis of the IoT Patent Registration Cooperation Network reveals 3 distinct clusters of individuals and companies actively involved in IoT patent registration. The first cluster, labeled Chinese Tech Companies, comprises 109 nodes, representing 1.44% of the entire network, with 493 edges and a density of 0.084, indicating a strong relationship between the nodes. This cluster is likely comprised of individuals working for Chinese technology companies active in IoT patent registration. The second cluster, European companies, consists of 107 nodes, representing 1.42% of the entire network, with 296 edges and a density of 0.052, indicating a moderate relationship between the nodes. This cluster is likely comprised of individuals working for technology companies based in Europe active in IoT patent registration. The study analyzed 3,697 patents related to IoT technology over the past 6 years, categorizing them into 6 technology categories. The IoT Patent Registration Cooperation Network was created to identify key individuals and companies, and community detection techniques were used to identify active groups in patent registration. The analysis of the patent's technical maturity using the Sigma plot program reveals that information services technologies are in the saturation stage, while smart homes, buildings, and smart grid technologies are in the growth stage. 3 technologies, safety and security, public safety, and environmental monitoring, and collaborative aware systems, are in the maturity stage. The study highlights the importance of cooperation between individuals and companies in joint patent registration, with an average degree of 4.572 and an average weighted degree of 6.83. The findings of this study can be useful for organizations and individuals involved in research and development of IoT technologies, providing insights into the current state of the technology and its potential future direction. Future research can build upon this study by examining additional patent data and applying different analytical techniques to gain a deeper understanding of IoT technology trends. I'm happy to help. However, it seems that you didn't provide the content to refine. Please provide the original transcript, and I'll be happy to refine it according to the guidelines you specified. The refined version of the transcript starts directly with the content, focusing on the key points and technical details of the research paper. It aims to maintain the accuracy and depth of the original text while ensuring it is concise and suitable for voiceover narration. This paper presents a comprehensive review of recent studies in social network analysis, text mining, and technology forecasting. It begins by discussing various methods for analyzing user behavior on video platforms using social network analysis, such as identifying key players and themes in SEO authorship networks related to AI applications in human resource management and sustainable supply chains. The authors then delve into the realm of text mining, highlighting its importance in business libraries and its potential for knowledge discovery. They discuss efficient text document clustering approaches, including those utilizing multi-search arithmetic optimization algorithms and nature-inspired optimization algorithms. Furthermore, the paper explores the use of patent data for technology forecasting, with a focus on China's RFID patent analysis and the exploration of technology opportunities and evolution in IoT-related logistics services. The authors also examine the application of social network analysis in capturing the salient aspects of IoT research, identifying technological trajectories in the mining sector using patent citation networks, and analyzing the research landscape of Industry 4.0. Throughout the paper, the authors emphasize the significance of these methodologies in understanding complex systems and networks, identifying key trends and patterns, and informing future research directions. They highlight the importance of interdisciplinary collaboration and the integration of different analytical tools to gain a deeper understanding of various domains. The paper presents a comprehensive review of recent research on the role and challenges of technology in creating smart, sustainable cities, focusing on the use of information and communication technology, ICT, patent data. It employs topic modeling, classification, and time series analysis to identify key themes and trends in this field. The study highlights the importance of understanding the structure of the Internet of Things, IoT, patent network, which can be achieved through social network analysis. In addition, the paper discusses various methodologies for detecting topics in social media using word embedding-based clustering. This approach allows researchers to identify and categorize relevant themes within large datasets, providing insights into public perceptions and trends related to smart city technologies. Moreover, the authors emphasize the need for effective user interfaces for managing and refining related patent terms. This is crucial for facilitating the retrieval of research datasets and improving the efficiency of data analysis processes. The paper also explores the application of unsupervised K-means clustering algorithms in analyzing IoT research patterns and trends. This statistical method enables researchers to group similar data points together, helping to identify distinct clusters or categories within the dataset. Furthermore, the study examines the potential future applications of IoT in the construction industry, highlighting its potential to enhance efficiency, safety, and sustainability in building projects. It also compares different service discovery approaches for IoT, evaluating their strengths and limitations in various contexts. The paper concludes by discussing the challenges and applications of IoT in smart homes, emphasizing the need for security-enabled safety assurance frameworks to mitigate potential risks. It also presents a technology lifecycle analysis of Persian lime, utilizing patent data to understand its development and potential future directions. Finally, the study surveys IoT applications in public safety management, demonstrating how these technologies can be leveraged to enhance emergency response times and overall public safety.